This is a video on how to fix, not replace, the select knob and any other digital encoder knobs. The scope that we're working with is a TDS460A. It was made in 1996. And before we jump into it, there's some things I want to cover that are special to this technology that'll help you out if you've never done a job like this before. On older oscilloscopes, the ESD protection the chips have is much less than in modern technology. All the older technology contains lead-bearing solder, and lead is toxic and it's been basically outlawed. When the sleeve is off of the oscilloscope, the fan is unable to circulate air throughout the whole oscilloscope, and parts of this will get very hot quicker than one might expect. Fourth is X-ray radiation. When you're working on a CRT, it's an issue. Take the appropriate precautions. And finally, there's electric shock. Not only are you dealing with mains voltages in a piece of equipment like this, but you're also dealing with the high voltages used to create the X-rays, used to put information on the CRT. Don't look at this video as a safety guide. I'm doing things in here just to provide you with information.
I started by pulling out the back 4 screws, which take a T15 Torx bit. Then I removed a screw near the front, which enabled the metal sleeve that goes around the oscilloscope to slide right off. The final step was popping the 4 plastic tabs that latch the cover on. To do this without breaking the tabs, since they're old and brittle, I used a small screwdriver to get underneath the tab instead of relying on the part that's easily accessible. Next, I undid the connector for the floppy drive and the one screw holding the floppy drive in and pulled it out through the front of the machine. This gave me access to the panel that housed the select switch. I popped the panel loose with a screwdriver and had access to the terminals of the switches. To see the output from a normal digital encoder, I connected the probes to the encoder used for the trigger signal, and I got 2 clean signals that were between 0 and 5 volts. If we stop and look at the signals, we can see them counting in gray code from 00 to 10 to 11 to 01. But when I looked at the signals coming out of the digital encoder for the select knob, I found that one went between 0 and 5, and the other went between 0 and something around 1.7. It also had a lot of noisy spikes. That told me that the problem was most likely in that digital encoder. To investigate further, I pulled the cables out of the control panel, and since they're old plastic, I popped the tab out with a screwdriver carefully and then wiggled them from side to side. With the board out, I was able to see the part numbers for the switches, which I'll blow up here. I don't know whether or not they make this part anymore, but if they do, I didn't find it. Each of the digital encoders is pulled up to 5 volts by 10K SMD resistors. From Ohm's law, this tells me that I'm looking at a short circuit across one of my switches of about 5K in resistance. To pull the switch out, I started by pulling the knob out, and I couldn't do this for all knobs, but for the ones that I could, I pushed down on the inner locking tab so they'd come out with less force, again just because of the age of the plastics. And I unlatched the tabs on the back of the control board and pulled it out, keeping in mind that there is a jack for the compensation signal. Before going too crazy with the unsoldering, I put down an index card since there are a lot of contacts on the board, and I didn't want to splatter rosin on the contacts and have to open this back up. Once the encoder was desoldered, I pressed the tabs together and pulled out the encoder. Then to open the encoder and figure out what was going on with it, I used a razor to cut around the 4 raised molded bumps, or whatever you want to call them, that hold the back of the encoder onto the housing. I left enough material sticking through that I could put the encoder back together in a somewhat secure fashion. And then I evenly lifted the encoder out of its housing, exposing the metal pads. Just for a sanity check, I measured the resistance between the inner ring and the terminal where I was seeing the low voltage. And I got 4.75 kiloohms. At first I thought this might be caused by metal residue, maybe mixed in with the lube that's used for these switches, that could have gone a little bit conductive after, I don't know, about 30 years of use. So I washed everything off with a Q-tip, but when I measured it again, I found really no change in the resistance, meaning that somehow an internal short had formed. So the first thing I tried to do was use a 12-volt regulated power supply to burn that short out. I soldered wires to the digital encoder and connected them to the power supply. After turning the power supply on, I measured an increase in resistance up to about 8.5K, which didn't really fix the problem. So I used a microwave oven transformer that I had rewound as an inductor. Instead of trying to stick a voltage on the primary, I just connected a D-cell battery to the secondary and let the spikes in voltage that occur after I remove the battery blow the gap out of the switch. After doing this, there was no measurable resistance across the two contacts. Just to be sure, I repeated this with the 12-volt supply supplying current to that inductor instead of the D-cell. Before reassembling the rotary encoder, I carefully cleaned off the brushes for the contact. These aren't one piece of metal, they're multiple pieces of metal that are maybe about 5 times as thick as a hair. So I spun the Q-tip in the direction that those little tines were facing. That way it wouldn't leave lint behind. Then I put bulb grease on the digital encoder. And instead of smearing it around with a Q-tip, I used something that wouldn't have any lint, wouldn't leave any residue in the encoder. Finally, I pushed the encoder mostly back together and used hot glue to go around the sides of it. I didn't squeeze the hot glue into the crevices or anything like that. I just dabbed a little bit so that it wouldn't get so far that it touched the contacts. And then I used the side of the heater for the hot glue gun to melt the hot glue while I pushed it together. After it had dried, I was able to rub the major excess off. And then I checked the encoder with a meter to make sure that it was working as expected, going between about 0 ohms and unmeasurable resistance before actually putting it back into the oscilloscope. Before doing a full assembly, I put the control board back together and stuck it into the oscilloscope to make sure that everything worked. The assembly process from there was pretty straightforward with one exception. Some of the cables on this oscilloscope stick up, so when you put the metal sleeve on the oscilloscope, it's easy to catch them. I caught mine, but fortunately I didn't close the sleeve onto the oscilloscope with enough force to go into the copper.
Hopefully you found this video useful and informative. If you'd like to see more videos like this, like and subscribe.